I know we've been talking quite a bit about RIP, and I've even told you quite a bit about EIGRP throughout the course of this event, but I do want to formally right now wrap up some information that we definitely need to know about these routing protocols if we want to be proud CCDAs. So let's go ahead and focus in right now in this lesson on the routing information protocol and the enhanced interior gateway routing protocol. RIP version 1 is not officially a topic that the CCDA covers. Well, it kind of is, though. I mean, they could certainly ask you questions, and RIP version 1 will be one of the possible responses, right? So, I mean, it's definitely something we want to know about. What we should focus on, too, is the shortcomings of RIP version 1. We really should focus on its shortcomings. And by the way, this goes a long way towards helping you understand what's up with RIP version 2. If you know the shortcomings of the first protocol, then you'll know what's so exciting and great about the second protocol. One of the things that we find is RIP version 1 is classful. We really didn't talk in the last lesson about the difference between classful and classless, and it's this simple. RIP is classful because it doesn't send subnet mask information in its routing updates. Uh-oh, not good. If there is no subnet mask information in the updates about prefixes, then a consistency of the prefix that you're using is assumed. You better be using the same prefix for all of your major networks, and that is where we have the problem with a lack of variable length subnet masking. It seems almost preposterous to us now, doesn't it? For a routing protocol to be classful, to not send subnet mask information when it sends updates about a prefix. I mean, for those of us that have been around these technologies for a while, we can't even fathom this. Yeah, RIP version 1 is classful, no subnet mask information in updates, and as a result of this, no variable length subnet masking support. Something else that is very strange to us is that it broadcasts its updates. Oh my goodness, how silly. A router not running RIP has to sit there and it has to be bothered. It literally has to be bothered and look at that update and realize, oh, wait a minute, I'm not running RIP. I'm not running RIP, so I really don't care about this particular update. How silly for machines that are not running RIP whatsoever to pay any attention whatsoever to these updates. So we are going to want a situation, of course we are, where the routing protocol uses a multicast approach. If it uses a multicast approach, well then we're in much, much better shape. With a multicast approach, it's only going to be those devices that care about the update that actually pay attention to it. Multicasting, it's like the concept of subscribing. It's like the devices are subscribing in order to hear the RIP information. You're probably not surprised that the pathetic little RIP version 1 doesn't allow authentication either. So there's no element of security that we can add directly to the routing protocol to make sure we're not sending information to devices that we shouldn't send information to. So when you examine RIP version 2, you do indeed see that many of these shortcomings are addressed. It is classless. Subnet mask information is sent in the updates so that we can do variable length subnet masking. And it does support authentication so that we can make sure that the person that we're sending the information to is an authorized person to be receiving that information. It multicasts instead of broadcasts. That's wonderful. And then it engages in a little bit of an annoying feature. It wants to automatically summarize your prefixes for you on classful boundaries. Let me go ahead and explain this automatic summarization behavior. And as a matter of fact, let's cover a real problem that this automatic summarization behavior can instill into one of your designs. Watch this situation. If we have some router like R1 here, and R1 can connect to, let's say, 10.10.10.10, 10.10.20, 10.10.30. These are all networks that it has connectivity to. And then there's some network, a router in the middle, another router, this network over here on the side, 10, 10, 10, 40, 10, 10, 50. Yeah, you get the idea. Now, there's other networks in between here, like here's 172.16, here's 192.168. Notice there's this change in classful boundaries. RIP version 2 by default, and version 1 would do this, but these RIP protocols, they are going to automatically summarize. So we're going to get this summary going from R1, and if you look at what R3 is going to do by default, it's going to do the automatic summarization on the classful boundary, and we can see a real problem here, can't we? Look at the R2 device. It's going to be really confused. If it gets a packet destined for 10, 10, 10, it's going to want to send it that way and that way based on these automatically summarized prefixes that it has received. This is the problem called discontiguous subnets. And of course, we have it compounded by the fact that we're doing automatic summarization in the protocol. So we have discontiguous subnets here, and we're automatically summarizing those discontiguous subnets, and we got a problem. So solutions to this particular issue revolve around, well, don't do the discontiguous subnets in your design. Get rid of the discontiguous prefixes, the prefixes for subnets that are separated by these, by these other networks. Or, of course, leave the discontiguous subnets in place and get rid of the automatic summarization. Obviously, both of these are options for us, and in RIP version 2, we can easily turn off the automatic summarization behavior. Something else that's interesting about routing information protocol is that it is going to rely on a series of timers, and Cisco has actually added some timers that weren't originally specified in the RFCs for RIP. So Cisco took it upon themselves to kind of enhance the timer utilization a bit. Cisco says, all right, we're going to recognize some timers that aren't ordinarily recognized for RIP. One of the ones that they built in was a hold down timer for RIP. We talked about the hold down timer before. This is where the device is going to be stubborn. As a conservative loop prevention mechanism, it's not going to listen to any updates about a prefix for some period of time if the prefix's metric has been reported as worse. Also, something interesting with RIP is that there is this update interval, right? So we're going to be sending out updates every 30 seconds by default. You've also got an invalid timer. In other words, if there hasn't been a prefix update for a while, that's that invalidation timer approach that we spoke to you about. Also, when does a route get flushed from the RIP table? There's a RIP flush timer to control that. And there's a brand new RIP timer that Cisco has added. Most of you in the audience, I bet, have never heard of this. It's called a sleep timer. It's a brand new timer that Cisco's added, and this can add a delay to triggered updates. Yeah, it can add a delay to the triggered update procedure if you're finding that the triggered updates are causing some problems in your environment because they're happening too quickly. Weird, but it could happen, I guess. By the way, the sleep timer, no way that would be in your CCDA exam. That's just too new of a technique and a technology to appear on your exam. I just wanted to give you that information so you had complete info when it came to the various RIP timers. Well, I'm sure you feel very educated about the RIP protocol. Let's now turn our attention to EIGRP. Yeah, we've talked a lot about EIGRP as we've moved through CCDA already, but I do want to make sure that we kind of stop and smell the roses here and summarize the design information we know about EIGRP for you. Remember what we said, it is very, very unique. It stands alone in the IGPs in that it is the only one we consider a hybrid. No, we're not talking about a car that's really, really good on gas. We're talking about a routing protocol that takes the very best features of distance vector technologies and then takes the very best features of link state technologies and puts those all together in a very robust, very fast converging protocol. By the way, something I have failed to mention, as we describe this particular protocol, it starts sounding like, oh my goodness, it's the best thing ever. Well, remember that it's Cisco proprietary. We know that proprietary is a really bad word, isn't it? Cisco proprietary means that for the most part, it's only going to work on Cisco equipment, and that is a major design consideration for us. If you're setting up a design and it must involve a whole bunch of different routers from different vendors, EIGRP is going to be a rough one because, again, it is a Cisco proprietary invention. By the way, EIGRP, it's got no class. You can't take it to a fancy restaurant. It would embarrass you for sure. We actually know classless is a good thing, and it allows for that variable length subnet masking approach that we utilize in robust scalable networks. Amazingly enough, it's a big surprise, like RIP, it does want to do the automatic summarization. But like RIP, it's no big deal for us to go ahead and turn that off. Now, the algorithm that EIGRP uses is called the diffusing update algorithm. And you know what? To be really accurate, I should have put that in all uppercase, because dual, D-U-A-L, is actually an acronym for the diffusing update algorithm. The diffusing update algorithm is really, really the most exciting feature of EIGRP. It's really why the protocol gets such a great reputation as an interior gateway routing protocol. How dual works, a nice, very, very quick summarization for you, no pun intended, of the diffusing update algorithm. What's so exciting about it? Let's take a look. What dual does is it has a topology table. It has what's called a topology table. And it puts all of the possible prefixes and how to get to those prefixes in this table. And what it does is it will go ahead and identify a best prefix. This is called a successor. And it will take this successor prefix and it will put it in the routing table. So you've got an identification of the very best route, and this is called the successor, and it puts that successor in the routing table. Okay, not very exciting. As a matter of fact, This is how a lot of different protocols work. They'll have a topology database. They'll go in, find the best route, and they'll move it to the routing table. BGP does this, for example. OSPF does something similar to this, for example. So what's the big deal about this diffusing update algorithm? Well, EIGRP does something really cool. It goes in and it identifies second best routes. These are called feasible successors. Or maybe there's just one. It's called a feasible successor. It doesn't put those in the routing table until there's a loss of the best route, and then it can immediately, almost immediately, it installs the second best route. So this is pretty exciting, very sophisticated, and it is how we can have such blazingly fast convergence with the EIGRP protocol. So there's a successor, the best route, that's moved from the topology table into the routing table. And then there is a second best, or even more than one second best routes that are identified. They're called feasible successors, and they'll be almost instantaneously installed in your routing table if there should be a loss of the successor route. So Dual, the diffusing update algorithm, really shows off with that capability of utilizing those feasible successors. Something else EIGRP can do, it's the only IGP that we have that can unequal load cost balance, unequal cost load balance across different paths. Wow. So you can go in and you go in with a command called variance, the variance command. And this command allows you to say, okay, I know this link is 1 meg and this link is 2 megs, and you wouldn't ordinarily load balance across them, but EIGRP, I want you to go ahead and do just that. I want you to treat this 1 meg link and this 2 meg link identically, and I want you to load balance across them. As a matter of fact, you can go in and you can say, okay, look, I want you to load balance across the 1 meg link and the 2 meg link, and I want you to send 1 packet down the slower link and 2 packets down the faster link. I want you to load balance, but proportionately to the bandwidth that is available. Wow. So lots of flexibility in the load balancing with EIGRP. No other IGP offers us that level of flexibility. Something that used to be popular with EIGRP, but we really don't care about it anymore, is the fact that it can work with more than just TCP/IP, thanks to what are called protocol-independent modules. We just don't really care about this anymore because the whole world has embraced IP, hasn't it? So the fact that we can run EIGRP in order to route IPX, SPX, or Apple Talk, yeah, we really don't get that excited about this because IPX, SPX, and Apple Talk, these protocols are fading away. They're going the route of the dodo bird into extinction. So we really don't care much about EIGRP's ability to route for more than just TCP/IP. One of the nice things about EIGRP is it's real friendly with its neighbors. Yeah, it makes EIGRP neighbors and it exchanges information with them, and it does it reliably thanks to its own invention called the Reliable Transport Protocol, RTP. Don't confuse this with the real-time transport protocol that is used in voice-over IP environments, by the way. Reliable Transport Protocol makes sure that the neighbors can exchange their information in a reliable manner. And we already told you in this course that EIGRP not only looks at bandwidth, but looks at a configurable delay value when it decides upon its metric. Now, what's interesting is it's not just bandwidth and delay that it could use. Cisco allows it to use a load parameter. They also use it to, or they allow a reliability parameter. But Cisco says, don't ever do this. It's so funny. There's the load, the reliability factor. There's even a tiebreaker of MTU. If there should be a tie in the metric, then MTU will be used. But what's really hysterical about this is Cisco says, you know what? Even though you could turn on load, you could turn on reliability, please don't. Go ahead and just leave it alone at bandwidth and delay. That'll give you more granularity than you'll ever need. And if you were to turn on load and reliability in the metric calculation, you would actually make your network too unstable. The network would be constantly recalculating the EIGRP database information, and you could really, really ruin things for yourself. So we're going to take Cisco's advice, and we're going to stick with bandwidth and delay for the composite metric, and that's going to give us, as much granularity, as much flexibility in the metric as we could possibly need. Well, I hope you've enjoyed this summarization, again, no pun intended, of both RIP version 1, RIP version 2, and the Enhanced Interior Gateway Routing Protocol. I'm sure you're ready to ace this exam review style question. What is the name of the algorithm used by EIGRP for routing? Yeah, you're all over it. Seems easy now. We know that this is the diffusing update algorithm. It is abbreviated DUAL. And it is very, very sophisticated. It has this concept of best routes called successors moving to the routing table, and second best routes called feasible successors, which stay tucked in the topology table, waiting for that day when they may be needed in your routing topology.